This is example 15, and what it is asking is for the, let me find it here. Alright, a 30-inch long steel bar, so this is 30 inches. "30-inch long steel bar, 1.5 inches square, is subject to a tensile force of 50,000 pounds. We have 50,000 pounds. How much does it stretch? Use E equals 29 million psi. Alright, what I want to talk about is Hooke's law real quick. And I definitely think you should read over what he has put in here for strain. But strain in is total, I guess some people think of it as deflection, as how much the bar moves. Let's say I'm going to do it in graphical, not graphical, but just kind of sketching it out. This is your original L. So when you strain or you put a force on something, it might get a little bit longer. So this right here, that difference in length is your total strain. So that's what you want to do. Let's say that you have a 10-inch bar, and then you put it into, you stress it, let's say, or you put a load on it, and it ends up going to 10.1 inches. So your strain will be 0.1 over 10 inches, which equals 0.1 divided by 10 should be 0.01. So your strain will be 0.01. Hopefully that makes sense. I know you see these stress and strain. Strain really never, it wasn't intuitive for me when someone said strain. I was like, well, you know, what's that? Stress. Okay, I've heard stress in everyday life. I've never really heard strain. Everybody always said, don't strain yourself, but that really doesn't have any useful application of this. So anyways, Hooke's law is, this is modulus of elasticity. Or Young's modulus. That's, I was just double checking that. Yes, Young's modulus. And just need to remember this is stress over strain, stress over strain, stress over strain. And it's always going to be 29 million psi or 29,000 ksi for steel. For concrete they have a strange, not strange equation, but it's always going to differ ever so slightly based on the strength of your concrete. And then wood, I know, is not really, it's not linear as this is. Steel is the best because it is pretty much completely linear, and it's the material that Hooke figured it out on. Anyways, the thing is, as long as it is you haven't yielded and you're still in that elastic range where, I don't know if we've ever really discussed that, but elasticity is, you're going to see these type of curves where you have this right off the bat. It's like that, and then it'll hit its yield point and it'll kind of dip down a little bit, and then it'll kind of go up and like that until it completely fails. And you may have seen this quite a bit, and it looks like they're actually going to do this in the next chapter, but this is, oh gosh, there we go. This is strain, and this is stress, F4. There we go. In my books we always wrote stress like that, and a lot of times people will do F instead, so choose what you wish. But this is the yield point about right here, and what that means is every single time in this material that you see, and every material will have this type of yield curve, but steel, you will always see that it'll go straight up, and it's really straight. Actually, it's right here, but this is not imperfect. This is not the scale, but right at the beginning, if you load it, if you put a load on it, so this is, it's going up in your load, this is your stress, you're stressing it, your strain will also, so it'll deflect, as I would say. If you're pulling on a string, it's going to get longer, and it's going to be linear in this region right here. For instance, if you put a 10,000 pound load on it, it's going to deflect that much, you know. Well, let's use this. Let's say we put a 10 kip load on this 10-inch bar, and it deflected 0.1 inch. So your stress would be, well, however, let's say it's a 100 square inch section. So that would be 10 kips over 100 square inches would give you your stress. So that's what your stress is, and it's going up. And then your E, which your strain, would move accordingly. And if you double that, it would be double, because this is linear. Until you get to this point, this is called your yield point. This is what you'll see, you know, Fy. Usually, if it's the capacity, you'll say, well, the F is capitalized because it's capacity. And you know, well, that's the, if you've heard your, you know, 50 KSI steel, that's what that is. 50 KSI steel, or you can have 36 KSI steel. Those are your most typical, and a lot of things are just 50 nowadays because they refine the process so good that they always just make 50 KSI. So anyways, so this is where 50 KSI is. So all the time when you load it up to 50 KSI, the big deal is when you do that, it'll go right back down if you take the load out. And that's what the elastic is. You know, it's like a rubber band. When you load it, you unload it, it goes back to where it was. You load it, you unload it, it goes back to where it was. That's the elastic region. Very important. So you want to keep this design in the elastic region as much as you can, because it's not going to deform. I mean, if you overloaded it, you'll see what happens is the stress really doesn't increase, but your strain does. Meaning, if you overstress this, if you put it up this much stress, and this actually kind of will go up here, this goes on forever. So it'll be actually like that. But we don't have the room, so a lot of people just say it looks like that, and they don't make it to scale. But anyways, so you could stress it just barely over, and it would end up way out here. And when you do that, because this is called strain hardening, once you start straining it, sometimes it actually gains more stress capacity, as I would call it right now. So it actually gets strong. You can put more load on it, but look how much you deflected. Now you're way out here, and then if you let it go, it will actually follow this same. This is kind of Young's modulus right there. It'll follow that same down, that same ratio. So this will be your final. You have zero load on it, and it actually already deflected. Let's say, you know, this is a ½ inch or something, or maybe it's 6 inches. Kind of depends on what you're doing. But that is your stress strain curve, and very important to stay in this elastic region. Alright, on to it. This, as I kind of said before, is your Young's modulus. That your elastic, that ratio, that rise over run, so that would be a slope, is kind of your Young's modulus. So if you have steel, you know, steel is going to be like this, and maybe concrete will be a little bit less. But anyways, they're all pretty much linear in the elastic region. And your Young's modulus is, once again, you know, where's Young's modulus? Here it is, stress over strain. So rise going up over run, which will give you that line. So what Young's modulus is, it's for each material. It's going to be different, and it's going to show you that slope. So it's pretty much how much if you put on a load, how much will that material deflect. All right. Once again, we'll probably do some more videos on this subject, but I'm going to go ahead with the problem since we've gone pretty darn far in trying to explain that. And it shouldn't make this isn't intuitive stuff. It'll just come to you in time, and you'll kind of get it. But I wouldn't worry about it if you've never seen that before, and you're like, "Oh, what the heck just happened?" Don't worry about it. And once again, doing problems is going to help. Do problems all the time. And it just starts making more intuitive sense when you do the problems, because you start to get a sense for, oh, if I'm pushing on this much, then it'll be that much deflection or strain. So let's move ahead, and once again, this is tension. We're only talking tension here. There's no shear, there's no moment, there's only tension on this bar. So if you look at his example, not example, but their equation is PL over AE equals, PL over AE is one of those things you need to remember. And the strain, or total strain as they call it, I always call it deformation, equals PL over AE. And this is for compression or tension. Compression or tension. So this will not work if you have a beam like this, and you have, let's say, let's say you have a simple beam and you have a P, and this is your L, and your A is going to be your area of cross section, and your E is going to be 29,000 for steel, and always be the same for steel. This won't work. That has a different equation associated to it that I haven't memorized. I think it's something like WL, or 34 WL squared over 384 EI or something like that. Anyways, not the matter. It's not going to deal with it right now. And don't take that to heart, because I'm just guessing. I know it's like 584, something weird equation like that. I've looked. It's actually in your steel book. You have a list of stuff like that I constantly use. But once again, we're talking about tension or compression, and here's your equation you want. Kind of deflection or deformation, let's call it, equals PL over AE, and P equals your load, which, let's go back up a little bit. Alright, so we're looking for, what is the total deflection here? How much are we going to move, or deformation? Or as they call it, total strain. And we have, if you cut it right down the middle, you cut this bar, you're going to see that, oh, we saw 50,000 pounds. It's not, you don't add these, it's not 100,000 pounds, it's 50,000 pounds. So I would take heed when you're looking at, with deflection, a lot of times it's in inches. You're going to see KSI for your E is always in KSI or PSI. So you're going to stay in inches. This needs to be inches. A lot of people will work in feet, and they'll be like, okay, let's do this. And sometimes you'll run into a problem where you'll get a wacky number, and you're like, oh shoot, I forgot to change it to inches. Deflection and deformation and whatnot will typically be in inches. So let's change that to inches. Oh, it actually already is in inches. Good. 30 inches. The area is, what's 1/2 times 1/2? 2.25. Let's do that right here real quick. The area of this bar is 1.5 inches times 1.5 inches. Just so you're not confused where I got that number. And that's A, and then there's E. E is 29 million PSI. And when you do that calculation, you get 0.23, let's say, and that's pounds over inch PSI divided by PSI. PSI divided by, it's divided, PSI, pounds per square inch, divided by PSI is going to give you nothing. That's going to cancel out, and then 30 will be inches. So about around point, oh, I'm sorry, I messed this up. It's 0.23. This is 2.3 inches. This is what I got. I forgot the 2. And I'm going to look at his, and he got 0.230, so we're good. And that is your answer. That's how much it's going to move, or your deflection total. They say, how much does it stretch? So you can say it stretches 0.023 inches, which sounds reasonable.